could also meet online somehow, like Google Hangouts or something like that. So it doesn't have to be right in my office. All right. Although during office hours, I can't be online and have people come in, but otherwise, if it's time, we can make that work. Okay. So, lecture this week. I'm truncated somehow. I don't know how that happened. Well, we'll see how this goes. We're talking about maximum likelihood estimation. So this is not what you're doing on homework, although it actually is. Maximum likelihood is essentially a way of getting numbers for estimation. And actually, I should note, last class we had we talked about the homework for half the class, or a little bit over half the class. We had an hour of lecture at the end. We didn't cover all the slides. We want to just pitch those slides. All right? So least squares, you can go look at them. They're wonderful, let me tell you. There was a great little R demo. I was going to have you all guess the numbers, and it didn't work. So, but in the interest of time and trying to move forward, least squares, the reason why that was there was to sort of familiarize yourself with more of the regression line and more of what showed up, because in your ANOVA and regression class, least squares was the only thing used to estimate your model. And by estimate, we're talking about where do the numbers come from themselves. So maximum likelihood, on the other hand, is another method of estimation in statistics, and I would say it's the engine that drives most of the modern stat methods that we use. Pretty much everything that we work on has its first best pass at it was from maximum likelihood. Now you'll hear there's Bayesian classes. I know some of you have taken Billy's Bayesian, which I think is the title of the class, Billy's Bayesian Analysis, BBA. That is nice, and there's nothing wrong with Bayesian, but the tools that drive maximum likelihood are actually the tools that drive Bayesian as well. So here we're going to talk about maximum likelihood, and we're going to do so because a lot of our multivariate classes, at least the ones I've taught and seen the books on, don't talk about it. And one of the big things that maximum likelihood does is it gives us ways for testing models, or model comparison, model parameters themselves. Remember, the parameters of the model is beta. Even though we didn't talk about meaning for these, that's where all of your story comes from. That's why you write the methods, or the discussion section of your paper, right? That's why you find what you do in science. So this maximum likelihood gives a very consistent way of describing the results and why they are important to your field. Maximum likelihood also is, it gives us several other really nice things for free. Now I'm sounding like I'm selling maximum likelihood. It'd be Templin's MLE class. So one of the things that you get when you get to multivariate statistics is the ability to have missing data and not have it ruin your analysis. Right? So how many of you have had missing data before? What do you do with your missing data? I don't know. I don't want to talk about it. I want to say, listen, I've done really bad things with missing data. So you don't have to tell me. I've imputed the mean before. Yeah. I've dropped the entire observation before. All right. I've done other worse, really terrible things. It's okay. What we're going to see, we actually have a course on missing data. When you combine missing data with a likelihood, maximum likelihood, and it also includes Bayesian as well. If it's an outcome that someone's missing on, like you have a longitudinal study or repeated measures, and someone comes for 10 times, it doesn't come the 11th, that's fine. You could just take all 10 of the times they came and use that in your analysis. You don't have to do anything with the 11th. And it actually provides some really nice assumptions built in with that, some very, very strong assumptions. So I like maximum likelihood because if you use MLE, your missing data assumptions, the things that you have to assume to make your analysis believable, are a lot more believable. They're a lot broader, right? Your data can be missing for a couple more reasons, which is a little bit more valid than if you just threw the case out, or if you plugged in the mean by itself, or something along those lines. So I'm not over here to criticize, by the way. We're all students in some way, shape, or form. Right? So maximum likelihood, I teach it here because it's one of the things that differentiates, to me, this version of of multivariate from all the other versions that I've taught or see textbooks on. But the way that we do things with maximum likelihood when you get to other classes like multi-level or like longitudinal or like structural equation modeling, we just jump into these things, likelihood ratio tests or Wald tests or information criteria. What are those? Where do they come from? So I want this to be the background that you have to go into it, right? I don't need you to derive a maximum likelihood estimator. I did teach a class on that like last semester, right? Some of you were in it. That was pretty rough, right? So we're not going to do that. There's another class for that. But I want you to be used to what it does in the process because it does look a lot different from what we're used to when we're doing these squares. So what we're going to start off with is maximum likelihood or maximum likelihood estimation or estimators, MLEs, for general linear models. General linear model, that's what we just had on the quiz, a regression nova tied together. In here you'll see today we have the NLME package, the nonlinear mixed effects, or the LME package, the linear mixed effects package, in R. But we'll also use a different package called Levon as well to do maximum likelihood. And this is where the class starts to get weird. We're a little hamstrung by software to do the best version of maximum likelihood for everything that we want to do. So path analysis runs one way, but it has some problems with its effects. And to overcome those problems, you have to go out of your way to do other things. So I'm going to teach path analysis first, and then we'll do the other things later, but you'll see a little bit of it today. How we doing? Trying to motivate you? Trying to sell you maximum likelihood? Who's buying? No, sorry. My daughter's selling Girl Scout cookies, and I'm selling MLEs. What? Yeah, it's off, huh? I don't know how. Anyone know why that is? What did I do wrong this time? How about I do this? In my book for how Templin's rules of repair, appliance repair, it's turn it off and turn it back on again. That usually resets the problem. The next step after that is turn it off, hit it, then turn it back on again. Like physically hit it. That usually works better. Let's imagine we have 5 observations. We're gonna break this down to really simple analysis. 5 observations, and you're trying to hire employees from where for a job where IQ or intelligence quotient is important. So we have 2 variables here. Here are 5 people. There are their IQs, and then we also have a measure of how well they performed on the job itself. So you have over here a descriptive statistics for everything and how that looks. Here's how estimation works in a more or less sense. To get your numbers, and actually let me just ask you this. I always go back to this. So you go and you use SPSS or R or whatever your favorite stat package is, and it gives you numbers. Why do you believe those numbers? Right? Like if you it's got kind of a black box feel to it, right? If you were to I've actually had this happen. I put data into SPSS. I asked it to give me numbers, and it gave me a bunch of question marks. What? So I got on the phone, and I called my friend Bob's dad. Right? I'm like, Bob's dad, Jim Henson. Bob, not the Jim Henson, but A. Henson. And I'm like, hey, I can't get this to work. What do you think beta 3 should be? And he was like, it's 2. Right? And so he gave me all my betas in that way. What do you think beta 0 will be? Oh, I think that's 10. 10, definitely 10. Okay. So in some respects, I got on one black box and it gave me question marks or it gave me numbers. And I got on another one, it was my phone. And on the other hand, there was a guy saying, yeah, 10 or 3. Which one do you believe more? Have you ever thought, why do you believe SPSS? Or why do you believe R? Actually, some of you don't believe R, that's fine. Been told you get what you pay for. In that case, you probably believe M+, which costs a lot more money than R. Anybody want to go with it? No? But you believe it, right? It came out of the box, therefore it must be. And that's why estimation is something that is important. So estimation is what will distinguish, or the properties of estimators themselves is what distinguishes belief in the software that you're using from the belief in Bob's dad. Right? Because in the long run, what we should know if we did things over and over again, is that Bob's dad probably isn't going to be as accurate, probably isn't going to be as not only precise, but just as we get bigger data, he might not even change. Who knows? But we may know something about our estimators themselves. So estimation is critically important in statistics. Like how you estimate a problem is really big deal. You never hear about it though, right? Did you think about it? I mean, aside from, oh yeah, we're using least squares, we're minimizing the squared distance, blah, blah, blah. You ever hear about that in regression and ANOVA? Not really, right? That's because in regression and ANOVA, the estimation process is well understood, and the properties that come from it in least squares actually dovetail with what we get with maximum likelihood in that one case, in the univariate model, when you only have one outcome. When you get to multivariate models, though, maximum likelihood, least squares doesn't necessarily give you the best results, and so maximum likelihood does. So that's what we talk about MLE. It gives us results that we know how they behave, so that we can trust them. We can trust the software itself. Now, we still can't trust whether or not, you know, if I was working at SPSS and I've made a lot of mistakes in my code, you still probably couldn't. There's still the chance there's a bug or something like that, but it gives you a little bit more belief in what's happening. So here's how estimation works, generally speaking. We minimize something. Right? What is the something? It's usually called a loss function. Right? In your typical linear model, with ANOVA and regression, it was the squared distance between the predicted value and the actual data. Right? So if you tried a bunch of betas out, you can make everybody have a predicted value. You could get the squared distance between their predicted value and their true observation, and then you could try again with another set of betas and do the same thing until you figure out the set of betas that give you the smallest distance, right? So that squared error difference is where least squares comes from. We want the least squares, or the smallest amount of them themselves. That's what we're minimizing. You do see least squares in multivariate techniques. Sometimes they come in the words generalized. I like the word ordinary. Ever heard of ordinary least squares? It sounds so normal, right? I always think about like statistics. We do a terrible job of marketing, with naming things. So think about like if some of these might be names of children that you might have, right? I'm gonna name my kid Ordinary. Yeah, what do you think about that? Hey, Ordinary. Weighted. That's not a good name, right? Diagonally weighted. I kid you not, these are actual names of estimators. There's one called WLSMV. If you're used to M+, that's actually what comes out of it. Weighted least squares, mean variance transformation, iteratively reweighted, and on and on and on. What we do in multivariate statistics is that these estimators are often the last resort. Right? If you have a problem that has so many variables or so many dimensions that the computer won't run in a very quick amount of time, and I'm talking like weeks or months, it does happen, then you find a way to shortcut it, and the shortcut usually comes in least squares. Right? So that is, last week we didn't present the slides, sort of like your ANOVA regression experience back in the day. This week, the opposite. We're going to maximize something. Right? Here we minimize the squared distance between each person's predicted and observed values across all the people. The thing we're maximizing is something called a likelihood function. And it works very much like the distributions worked last week when we talked about heights. Right? We plug in a piece of data, we plug in like the mean or the variance, and we figure out the height. Right? So that is the basis for a likelihood function. We combine it across people, and then we can go and figure out, if we plug in a mean, what's the height? Plug in the variance, what's the height? Well, it turns out the mean we can replace with all of our betas, right? We do the same thing over and over and over again. So maximum likelihood, we're going to try to find the maximum likelihood of the likelihood function. Often, sometimes we abbreviate that with ML. Residual maximum likelihood is another version of it. Still maximum likelihood, but what we're maximizing is a slightly different feature. Often we call that REML. We don't call that MOL, we just call it ML. Get it? I guess that's the difference between an acronym and an initialism or something. Have you heard that word before? I've heard before that if you cannot pronounce it, you can't call it an acronym. I tend to like work and know people who know lots about language in grammar, and I don't. Robust ML, another version of it. How about that? Robust. Is that a good kid name? Robust. Anyway, so that's what we're going to talk about today. These are the gold standard of estimators. Not next week. We're going to learn why today in a few slides. So that works well. Hang on one second here. Pointer options. Yeah, we'll forget it. Finally, the last way that we do things. So these two ways we're trying to find, we have one function, although we've got a bunch of parameters in it. We're kind of guessing our way through the parameters to figure out the maximum or the minimum of a function. The last way is to sort of use another version of this likelihood function and simulate, right? Randomly draw parameters from what their distribution should be. Which is an odd way of saying it, but this is what we call Bayesian usually, Bayesian methods. We could actually maximize Bayesian versions of likelihoods up here. They're called maximum opportunity. But down here, down here it's just to do a brute force approach. The names are involved Bayesian or Markov chain Monte Carlo. If you're in physics or chemistry, you'll call it Monte Carlo. You just won't drop Markov chain. There's Metropolis Hastings or the Metropolis algorithm. On and on and on. Metropolis sounds pretty cool, right? It's like Superman algorithm, right? That's Superman. Okay, awesome. Glad someone knows. Anyway, these last methods are generally built for complex models where ML is not available, and I'd actually say this is my favorite solution down here, because just like this guy Billy who teaches Bayesian, I believe very much in Bayesian statistics. So we're going to jump into maximum likelihood today. We will cover Bayesian statistics later in the semester. We'll have a class on it. A couple reasons why. Number one, it is an emerging method for estimation. It is nothing. Some people can be very afraid of it. There are ways of tricking the data in Bayesian. The other method for it is that when maximum likelihood won't save you with missing data, we can use Bayesian methods to do what we call multiple imputation. So we're going to make up data, but we're going to do so in ways that we can believe in statistically. So that's the main thing for it. How many of you have fudged data before? How many of you as advisors? Okay. just going to start getting into a whole bunch of hornet's nests here. Megan raised her hand. I've made up data before, but that's because I do a lot of simulations. Okay, good. We'll leave that go. Let that go and hope the recording didn't pick it up. So, why do we trust maximum likelihood? There are a number of reasons, but here are three big ones. If our data meets several assumptions, and these are a little bit bigger than assumptions. In fact, in the way things are written in statistics, they call them regularity conditions. Like, what do you think of when you hear the word? If someone were to stop you and say, "Hey, regularity condition," right? It's not pleasant, most likely. Again, statistics and naming, not a good combination. But if we meet these assumptions, then our MLEs have very good properties that are proven. This is one of the few places in science that you can say proof, because this is a mathematical formulation of things. One of those is something called asymptotic consistency. So here's one of the lingo terms. Whenever you see asymptotic, that means when your sample size goes to infinity, right? So as your sample size increases, what asymptotic consistency says is that the estimator, or the value that the computer gives you, converges to its true value. And this converges in probability means it becomes the true value with probability 1. So that's cool, right? That's one reason why you like MLE. Bob's dad doesn't have asymptotic consistency. But with an MLE, you know you're going to get the right answer should you collect as big a sample as you can get. The next question then becomes, where's infinity? Right? And that's actually an interesting commentary, because a lot of the MLE properties are based on infinity. But what functional infinity is and what actual infinity is two different things. Right? You remember the T distribution before? We all love T, right? Student. The T distribution in your basic stat class had degrees of freedom, and if you looked in the back of your stat book, or you went online to try to do a distribution test, as degrees of freedom got to like 25, it basically became a normal distribution, right? That's like infinity for the T statistic, right? It's not quite, but it's pretty close. That's what happens here. And what we'll see in multivariate statistics is as our models get more and more complex, we need bigger and bigger sample sizes to try to estimate them, to be able to achieve some type of sense of consistency out of our estimates. So, asymptotic consistency. Basically, we know we're going to get the right answer if we collect a big enough sample. Right? That's pretty cool. Who's going to argue with that, right? Political candidates, probably. Never mind. Trying to make statistics into something offensive, right? The next one, asymptotic normality. What? That means as you're getting closer to infinity with your sample size, remember infinity could be as low as like 25, the distribution of any parameter becomes more and more like a normal distribution. Right? Now if you're thinking to yourself, hey, didn't I just say the T distribution and this T kind of looks like normal, but as you get more and more degrees of freedom, it becomes normal. That's exactly what's happening. So what this ends up doing is that if we know a distribution has a normal, if we know our parameter has a normal distribution, and we know that the true value we get, or the parameter we get becomes the true value if we have a big enough sample, we can use this normality assumption to test any parameter to see whether or not, if we put a confidence interval around it, includes 0, whether or not it's significantly different from 0 itself. Right? This doesn't mean it doesn't matter whether you estimate a regression model with ML or you estimate the most complicated analysis model you've ever seen. This holds. It's cool, right? It gives us a way to test it. Now, the normal distribution, we know the mean. The mean is going to be used. We're going to use the actual parameter estimate for it. For the mean, the variance of that normal distribution actually comes from another property of maximum likelihood. Comes from something called an information matrix. It's actually the inverse information matrix. Gosh, it's a lot of blah, blah, blah in there. Don't worry about that so much. But the point of the matter is, again, whether you're doing regression analysis, whether you're doing a very simple model, like an empty model where we just get the mean and variance, or whether you're doing the most complicated structural equation model on the planet, you still have asymptotic normality. And it still works the same way. You can get an information matrix, you can get a variance, you can do a t-test or parameter test with your parameters themselves. So that gives you a chance. So this one tells you, you know you're getting the right answer. This one tells you, you know that you are, you know how to test whether or not your hypotheses are true. The last one says efficiency, that no other estimator has a smaller standard error. So what this means is that that standard error, that variance that you see to go around your parameter estimate, the MLE will have the smallest amount of error to it across sample size and so forth. So that means standard error smaller. If you use it in a hypothesis test, you're going to have better power. Right? So therefore, selling you maximum likelihood. If you collect a big enough sample, I should add, one of the conditions, one of these regularity conditions is you've got the right model. You can't like misspecify the model. But we assume we have the right model always, right? All of you have the right model. So if you collect a big enough sample size, you know you got the right answer, you know you can test whether it's significantly different from 0, and you know that nothing else will have better power from that, right? Yeah.
Why is it
gosh, I'm blanking now. It comes from there's a theorem in statistics. If you take a math stat, I'm so sorry. I'm saying that because one of the debates about what I teach next semester might be math stat versus something else. But there's several classical theorems that talk about how this lower bound of information gets achieved under these regularity conditions, and by that, MLEs guarantee it happens, but nothing can be lower than it. There's something called the Cramer-Rao lower bound. I don't know if you've heard of that before, but it's out there, right? It's pretty it's pretty whack, but it is something that you can show for it. In this regression analysis, like the betas we drew up here, they actually have a term for those. They're called blue estimates, or best linear unbiased estimates, and they're best because they have they're the lowest, they're the most efficient themselves. So I don't know if that helps at all.
Is it true even
Really?
Like, no. Is it true even considering like Bayesian estimation?
Now Bayesian estimation, it would still follow under Bayes, because the likelihood function that we're going to form with MLE is the core of what we get in the Bayesian posterior distribution as well. It's actually like they just relabel something. It's the same thing. So if that thing, if n goes to infinity, it behaves this way, then just multiplying it by a constant will do the prior will do the same thing. So yes, but it won't be better. Sorry. You think you want to argue about the best? Yeah, math stat. All right, how are we doing, everybody? Other questions? Have a lot? Is this? I mean, this is not the most exciting topic in statistics. Don't get me wrong. It's probably another reason why we don't teach it early on. I'm trying to make it exciting. We use MLEs because we think they're right. Gosh, I keep leaving these Fridays class crap in here. All right, so MLEs, the maximum likelihood, the thing that we're trying to maximize, where we get the maximum from, comes from the statistical distribution. And we saw statistical distributions in action last time. So what we're going to do is we're going to start with this normal distribution. Remember this function from last week? Right, that's our bell curve. Right? And for every value of x, if we knew what mu was and if we knew what sigma squared is, we could figure out how relatively likely any value of x happened to be, right? So the blue line, the most likely values are 0, or closest to the mean, and just relatively less likely as you get further out. That function right here, this ugly looking thing right here, it provides the shape of the line. And last week, and just on that next slide, we pretended like we knew mu and we knew sigma squared. But right now, today, we're not going to. It's the flip. Like when you collect data, you don't know mu. You don't know sigma squared. And mu looks a little weird, but if we go back to this regression line, we talk about this being the model for the means. That's what we're going to call mu. Right? So we're going to replace mu with a series of betas and other predictors and so forth. Conditional mu. So in maximum likelihood, or in regression analysis, if we use maximum likelihood, we're not going to know mu, because we're not going to know all the betas. And we're not going to know sigma squared, or in this case, sigma squared error. But we are going to know the data. We're going to know y or x, we're going to know z, we collect all that. So we're going to flip the likelihood on its head, right? If this function, if we knew mu and sigma squared, right, there's only a few unknowns here. Pi, by the way, pi is the number 3.14, that's not a parameter. Sigma squared and x. Those are the pi is a constant, so I'll just kind of scribble that out. So if you knew mu and you knew sigma squared, all you'd have to plug in is x and you'd get the line, right? We're going to flip that, right? We're going to say, what if we know x, right? And if we had enough of these functions, and we didn't know mu and we didn't know sigma squared, we still get the line, right? Right? If we plug in a mu, we plug in a sigma squared, we would get the line, right? In fact, if we look at this next graph, here, if we flipped it on its head, let's imagine we've observed x here, right? Well, what's the most likely mu? Well, here's a mu of -2. That's the green line. That's how likely it is to occur. What's the most likely? Here's the mu of 0. Right? The mu of 0 seems to definitely be mu of -2 for this observation. Right? So now the next question is, what's the most likely variance? We can go up and take a look. Oh, here's a variance of 5, here's a variance of 1, and here's a variance of 0.2. So if we're going to ask that question, what's the most likely, what's the most likely distribution, or mu and sigma squared, that gave us this value of x right here? We would pick the blue one, or 0 and 0.2. That's how maximum likelihood works. It takes that distribution function and says, what's the values that produce the maximum itself? Right? If our x was, let's say -2, actually -1, let's do that. That's a little more complicated. Right? Here, what is the most likely value? Well, it's the red line is the highest. So that we would say, given this data, mu of 0 and sigma squared of 1 would happen to be. Now this is a hypothetical example. If you only have one observation and you have two unknowns, you're never going to be able to find them both. Right? It's not going to be possible. But that's how maximum likelihood works. It flips this function on its head, says, I know the data. Let me plug in all the things I don't know and try to figure out the set of those that bring about the most likely value. And I hope this is helping conceptually. Right? You're not going to have a quiz where we're doing calculus. You're not going to have a homework that's doing calculus. You may have a homework that says, here's a function in R that tells you how to compute the height. We'll compute the height. So that's about as far as we get. I want more of a mental representation of the distribution than anything else. The nice thing about maximum likelihood is those nice properties that we see here hold whether or not this thing is the normal distribution or we switch it. Right? Your data aren't continuous? Great. We don't use this distribution. Right? If you've got binary data, we'll use something that says binary sample. But it works the same. And the properties still hold. So that's the nice thing about maximum likelihood. If you understand the core, that it works on distributions, and you have to pick that distribution, then you can use the same, you can pretty much use software that does, if you have count variables, okay, there's something called the Poisson distribution. There's actually something called the negative binomial distribution, right? I can't draw what the distribution is up there. I don't know, I have to go look up what the negative binomial function happens to be. But I can tell you how it works in ML, and I can tell you when I get my estimates, they have these properties. I know how to test their hypotheses. I know how to go and evaluate them statistically. I know that if I collect a big enough sample that they'll be pretty much right. So that's the cool thing. Are you sold? Not quite. Any non-believers out there? Aside from Jennifer. All right. So here's what I was telling you before. If this is the original version. If we had a distribution and we knew the mean was 114.4 and the variance was 5.29, we could tell the relative likelihood of two values in that distribution, right? So 114.4 is actually more likely than 110. That's the original way of looking at it. That's how we normally talk about distributions. ML does the flip. Right? So what we have to do to use maximum likelihood is we first have to build what's called the likelihood function. Right? That is the actual function that we need to form to figure out the maximum. The likelihood function provides a likelihood, or a height of a curve, for a set of statistical parameters. Right? So here, the likelihood function takes the data you've observed, and you try out a set of betas or a set of sigma squares or whatever your model parameters happen to be, and it gives you a likelihood, a value that tells you how likely that set of parameters would happen to be, a relative likelihood in this case, right? And just like we saw here on this previous slide, any set of parameters is going to give you a number like 0.173, 0.128. Your goal is to find the set of parameters that give you the most, the highest, the maximum. Those parameters are called the maximum likelihood estimates, the MLEs. The likelihood functions start with those density functions, or the thing that drew the bell curve here. This is a PDF, probability density function. Every distribution has one of those, and each person that you collect data, you think, oh, this person, their data had to have come from some distribution. I have to go and figure out or take a guess at the distribution. In our case, it's normal, but in other cases it may not be. But that's the kernel, that's the core of how MLEs work. The likelihood function then gets aggregated across your sample, right? so that everybody's individual likelihood function gets combined into one very big likelihood function. Right? Looks pretty ugly mathematically, but it's how the process gets driven. And if you can think, okay, I just need to plug in parameters and get height, it's the black box. It's trying to less of a box. It's more like transparent, or less black. Maybe it's more transparent, opaque. Maybe is that a good word? Not quite. No, still fuzzy. Still going to be fuzzy, but it's less unobservable. So sample likelihood itself is like this, what we would call a joint distribution across the entire sample of how likely all the observations were to have occurred in this data set at once. So let's consider one value here. So let's assume the following. We have observed the first value of IQ, which is 112. Okay? We are also going to assume it comes from a normal distribution, which means we're going to have a PDF that looks like that. That's going to be the basis for our likelihood function. So we know x, we know x, check, won't drop, x, we know the actual mathematical function, and we're also going to assume that we know sigma squared. Right? I'm only doing this because I want to show you how it works with one value. I can't get two numbers from one unknown, right? It's an underdetermined set of equations. I think that's right. We know x, we know sigma squared, we don't know mu. So what we can do is express this PDF a little bit differently. Right? This PDF, we plug in what we know. This is a function where we just have mu as the only unknown. So we can try out values of mu and pick the one that gives us the most likely result. Right? So for every value of mu, mu could be the likelihood function now gives us a number that's called that is called the likelihood. That is the number for it. And the value that is the value of mu that gives us the highest likelihood is our estimate. That is our MLE, our maximum likelihood estimate set. So what really this is like asking, what is the most likely mean that produced our data? So it's actually going to be pretty intuitive here. Here's our likelihood function. I literally did this in my syntax in R. You can see I actually go and try out values of mu really naively from like 100 to wherever, 125. I plug it in this function. Here's my likelihood function, right? Most likely value, the 0.173, that's the highest. That corresponds to a value of 112. So we would say that 112 is my best or my most likely estimate of the mean that gave me these data. I only have one observation. Happens to be 112. That is a sample mean of 112, right? Sum of x over n. Here, it's just x over 1. It's 112. It should be the same thing. So that's how it works. Pretty awesome, right? You know what's even more awesome? It's break time. So let's take a break. Come back about 10 minutes, and I'll sell you some more maximum likelihood.